Hi, in this talk, I will present our work, Seeing Wake Words, Audio-Visual Keyword Spotting. My name is Liliane, and this work was done in collaboration with Triantafylos Eforos, Temos Stafilakis, Samuel Albany, and Andrew Zisserman. The goal of the paper is to automatically determine whether and when a word of interest is spoken in a video clip. This can be useful for downstream applications such as wake word recognition, video search of archival silent films, or other human-computer interactions such as smart car or home technologies. Given a user-defined keyword and a video clip, our model first produces a two-dimensional similarity map, which highlights the alignment of the phonemes in the keyword with the visual sequence. The similarity map is expected to show a diagonal pattern when the keyword occurs in the input signal. This diagonal pattern can in turn be detected by a shallow CNN that determines whether and when the keyword occurs. In this way, the similarity map separates keyword spotting into two subtasks: sequence matching and pattern detection. Our method is zero-shot, meaning our model can be used to spot words that are unseen during training and specified by a user at test time. It can be applied for in-the-wild videos and can take as input either a visual-only, audio-only, or audio-visual signal. Our model can also generalize to languages beyond English, specifically to French and German. Now we will go into more detail on the following three topics. I will first show an example of visual keyword spotting, where we query the word advertisement in the following input video, without any audio information. Next, I will show where our model predicts the keyword to be. Note, there will be a color change. Finally, let's look at the ground truth video with audio and subtitles.
It's also come up with a structure that acts as an advertisement which says,
Some key challenges in visual keyword spotting include homophones. These are words which sound different but involve the same lip movements. For example, the words mat, pat, and bat cannot be distinguished without any audio information. Other difficulties include intra-class differences, such as accents, speed of speech, and mumbling, which modify lip movements, and variable imaging conditions such as lighting, motion, and resolution. Spotting words from continuous speech is also challenging, as there may be co-articulation of the lips between preceding and subsequent words. We now show some example similarity maps from our visual-only model. The input video is shown on the left at half speed. The corresponding clip transcript and similarity map are shown on the right. The queried keyword is underlined and in bold. For each similarity map, the horizontal axis is annotated with phoneme ground truth start times for clarity. Note that graphemes are actually shown here for simplicity. Let's take a closer look at the visual keyword spotting architecture. A sequence of frames of a talking face are encoded with a ResNet-based architecture followed by a BiLSTM. The phonetic sequence corresponding to the keyword is inputted to a BiLSTM phoneme encoder. The similarity map is then produced by computing the dot product between the visual and phonetic features. We then concatenate the phonetic sequence embedding to the similarity map for two reasons. Firstly, to encode the length of the keyword, and secondly, to encode whether there are repeated phonemes in the keyword, which may lead to off-diagonal components. Finally, this is passed through a fully convolutional detector that outputs for each time location the probability that the keyword occurs. The sample is predicted to contain the keyword if the maximum probability over the duration of the signal is above a certain threshold, and the position of the maximum is the predicted location of the keyword. Following previous work, we use a binary cross-entropy loss and form positive and negative clip keyword pairs, where for the positive pairs, the keyword occurs in the input signal, while for the negatives it does not. For training, we employ a curriculum learning strategy. We first pre-train on the LRW dataset, which consists of single-word utterances, and subsequently fine-tune on the LRS2 dataset, which is made up of sentence-level utterances. Both audiovisual datasets are built from BBC television programs and are publicly available. Now we compare against previous work on the LRS2 test set. Specifically, we consider two baselines, the state-of-the-art for visual keyword spotting and the state-of-the-art for lip reading on the same dataset. Our model surpasses both baselines with a mean average precision of 53.9%. Visual keyword spotting is valuable when audio is unavailable, but also when audio has been corrupted by noise, for example, from background music. We demonstrate a few examples of such a setting with plots of output detection probability from our audiovisual model. It should be noted that our model has not been trained in the domain of these movies.
Right now, all I can tell you is that you're in danger.
2 years later, the company's worth $500 million, and Roy Ray
tucked away $100 million. Been living the high life ever since he got out of prison.
Our audiovisual model is formed through a late decision audiovisual fusion. The audiovisual model outperforms visual-only and audio-only models for a clean audio signal, as well as a noisy audio signal for a range of signal-to-noise ratios. Finally, we generalize our model to other languages. We fine-tune the pre-trained models on the LRW and LRS2 datasets on LRS3 and LRS3 Lang, which are audiovisual datasets built from TED Talks. LRS3 is an English-spoken dataset, and we select French and German subsets from the multilingual LRS3 Lang dataset. We next show examples in French and German. Note that although the input to the model in this case is visual only, audio is included here for clarity.
De pouvoir croire à des grandes ambitions. Et ça, je voulais également pouvoir le transmettre.
Qu'on peut, en suivant les chimpanzés, aboutir à des découvertes intéressantes.
Voilà, donc je crois vraiment à cette idée que la création, elle peut être faite.
Die Plastik jene positiven Eigenschaften verleihen, die wir so an ihm schätzen.
Und der hat wirklich dieses wunderbare Buch geschrieben.
Bisher hatten wir so alle 10 bis 20 Jahre einen technologischen Sprung.
Thanks for watching. Please refer to the paper for more detailed numerical evaluations and check out our website for more examples.